Welcome to joint EOL and RAL seminar. Today we're going to be hearing from Vivek, who's Senior Scientist in EOL. And just a little bit of background on Vivek. He's been at NCAR for since 1991. But prior to that, he did his undergraduate degree at Madurai in India, and then a master's at the Indian Institute of Technology, and a PhD here in Colorado at CSU. He has a long history of radar developments in EOL. It's SPOL, HCR, APAR, but undoubtedly contributed to many other radars. He joined the NCAR initially in RAL in 1991, and then transitioned to a joint appointment with the EOL, and since 2006 or 7 or so, he's been just in EOL as a senior scientist. He's a fellow of the American Meteorological Society, editor of the Radio Science journal, and has received various awards like honorary fellowship from the Indian Meteorological Society and the Christian Hughes Medal from the European Geophysical Union. So please join me in welcoming Vivek. For those online, please present your questions via Slido, which you'll see on the presentation page if you scroll down. Thank you.
Okay. Thanks, Bill. Thanks for a kind introduction. Today, basically, I'm talking about geophysical signal measurement, but I'm focusing on mainly radar. But at the end, I will show you what the geophysical measurement also mean, radiometers and other things. The first part, most of the time, my talk will be on the radar at this point today. My co-presenters, So Wang is in the audience here. Eric Lowe is on travel, on calibrating a radar somewhere, I guess. So he won't be here. So, give an introduction. The radar, the weather radars are more than 50 years or 60 years old. The techniques are very well established. What we collect, the time series, which is radar signal, that's called level 0 data. Then you process that, get the radar products, then produce a product from that. It's a level 3, level 4, like that. It's pretty much set, not much big change. All you measure is radar signals, you do all the processing. In this talk, I'm going to show you, you don't have to measure all those signals. It's good enough to measure a subset of what you measure. Then using the AI, you can synthesize the data so that you have enough samples to get the data. Your introduction here. The radar basically transmits a bunch of pulses. Typically, about 64 or 100 samples are taken, get the radar returns back, because the signals are fluctuating. They're Gaussian random processes. So you have to average out the radar signals to get anything useful out of that. And so it takes a bunch of measurements for a given ray, average it out, then get into radar measurements. That's called a time series. It takes data one after other like that, every millisecond or every microsecond, how I do it, depending upon how a tenth of a millisecond. Say, we are familiar with some of the products like this. In this case, what we have is radar dual Doppler winds imposed on reflectivity here. This is the height. It's a cross section here, basically here, the distance. So this is called basically, the DBZ is called basically level 2 product, sorry, level 1 product. Then on that, we got a product called a wind measurement, like a level 3 or level 4, like that. And these are the product we deal with that. They're not level 0. Today I'm going to talk about level 0 data in the radar measurements. Similarly, if you look at S-pole radar, what we have is a cross-section. It's about 15 or 18 kilometers, cross-section of thunderstorm here, the distance here, 70 kilometers here. This is, again, a level 2, level 1 data, dBz values. Above that, there is an overlay of particle types, ice and rain and all insects, all those things. These are like a level 3, level 4 products, and that's what we deal with that most of the time. This is an example of a cloud radar. The cloud radar is a 94 gigahertz radar. It's a 3 millimeter W-band radar. Where we have is a product. This is the distance, about 5 minutes here. As it goes through it, this airborne radar. This is the altitude. What you see is a product. Basically, it says a cloud to drizzle transition, drizzle and rain like that. This is a product. What we derive from these measurements, these are the measurements, what you do that. The reflectivity, radial velocity, spectrum width. These are the input goes into that. It's a level 2 measurement, basically level 3 or level 4 like that. These are the typically what we do that. In addition to that, we can also create a products like this. This is again a radar measurements. The radar measurements here, what we have, the same data what I showed earlier. Here it shows a particle size, what you derive, the micrometer in a cloud, like that. Then also in gram per metric per liquid water content. These are all the products what we use in day-to-day science mode. But we are going to talk about today level 0. Not many people use this data, radar engineers use that, but that's where the thing I'm going to show today is going to be interesting. I had to put a background on this. The radar, what we have is a frequency standard, a GPS standard signal. From there, we have basically a, say 3 gigahertz, the shallow, and 60 megahertz is a IF frequency. We mix it, and power amplifier, it's a klystron or a magnetron. We transmit the signals like that. Then get duplexer, signal returns back here, low noise amplifiers, get basically a mixed with the shallow, come back to a IF frequency here, I and a Q. The I and the Q are the radar level 0 data. This is called in phase and quadrature. This is the root for all the radar what we do it. From this, we create wind, reflectivity, or a product, everything else. This is the I and Q. This is the in phase quadrature. This is basically a complex signal what get measured. Now, this signal has a characteristics. Hydrometers are randomly distributed in a cloud. There is no specific location for that. Typically in a raindrops are about 5 to 10 centimeters apart in a typical rain. You got about billions of raindrops in about 200 meter resolution volume in the radar. That's why the 1 degree beam, 200 meter, billions of particles. Radar echo comes from all of them, backscatter here. Let me see. I don't see that arrow. Okay, here it is. Okay. The sum of the backscatter signals are randomly distributed hydrometers. The central limit theorem says sum of all those independent signals are Gaussian random variables. It's a very standard. If you look in the book about radar signals, that's what you see it. It's a Gaussian random variable. Hence, anything we measure in the radar, it takes a lot of samples, either 64 samples or 100 samples to average out, get radar observation. Now, if you describe that, the I and the Q, what I showed in the previous thing, the in phase, the quadrature signal, the radar signal we talk about here, is a voltage. That's a time series, a function of time. It's about 64 samples, 128, or even thousands in the case of wind profilers. It's all of them are a time series, that's all to it. I and Q are independent zero mean Gaussian, just because these particles are randomly placed in a sample volume. And there's basically it's zero mean Gaussian. The power is sum of the voltage, I squared and the Q squared. If you take one sample, We don't average out. One sample of the radar signal, if we compute a power estimate as a relative error about 100%. That's why we average many samples so that we get certain accuracy. So one sample exponentially distributed, and because 100% error, hence we cannot use that. We got average number of samples. Hence it takes certain amount of time to collect the data set. Typically, it takes about 5 to 6 minutes for a volume get covered by the radar, even the faster scanning. It takes time. If you scan faster, then you don't get enough samples. Your measurements are more error. Hence, you got to scan slow, at least have enough samples. Hence, there is a challenge, what you do here. We can't do too fast. If you do fast, then you don't have enough samples. But at the same time, everyone desires, I need a good measurements. There is a balance. The technique what I described today, going to show, you don't need all those samples. Still, you get a good, accurate measurements. That's what this talk is about. Okay? Now, statistically, the I and the Q, these are the signals here. In-phase signal, this is basically a histogram. You see that Gaussian distributed, the I and the Q. And the phase is a random, minus pi to plus pi, basically random signal here. And that, again, by statistics can show the power is exponentially distributed. This is a very well-known characteristics of radar backscatter measurements, whether it's a profiler or it is S-band radar or HCR, they're all the same thing, there's no difference. Then this is a basically histogram of all those. These are about 10,000 samples I have in this histogram, what I simulated, right? Simulated measurement. Now, how does it look like one of them? It will look like this. This is the time. This is the voltage in phase. This is, we got about 64 of them, 64 milliseconds here, what we have. This signal simulated for velocity of 14.6 meters per second, spectrum width of about 1 meter per second. For that, I simulated a radar signal back. The 64 sample, that's all look like that. It's called time series. Now, the talk here, what I'm going to give is, can you predict this time series? That's the problem here. That's what the challenge here. Somehow, we have been measuring I and Q for more than 55 or 60 years. I doubt anyone attempted to predict the radar signal so far. This talk shows that. Now, this is the I signal, the Q signal. Both are a time series. This is the Fourier transform of this one. You see that this is a Fourier frequency here. This 500 frequency corresponds to about 25 meters per second. The 300 here corresponds to about 15 meters per second. That's what this one is about. And we know very well how to process all these signals using radar signals. How do you do that? This is how we do that. And so we know how to simulate radar echoes. You can Fourier transform, look at in time domain, frequency domain, you can do it. See, this is plus 14.6 meters per second. If I do a negative velocity, see here, how this is basically it's time series for a different velocity, minus 14. This is what means, minus means basically the storm is moving towards radar. Positive means moving away from the radar. That's how the notation is given. In this case, again, a time series, you see the Fourier spectrum of that one is shifted to minus 300 hertz like that. And these are all well-known characteristics of the radar, how radar measures the signal, how the Doppler is measured. This is corresponding to Doppler measurement, about 15 meters per second, that's same as here. See that 0.60 meters per second, see how narrow the spectrum is. If that spectrum width is broader, it could go up to 3 or 4 meters per second. That would be very broad. Okay? In this case, I took a narrow so that you can understand the math, what I'm working on. So we can see, this all simulations. Now, comes to radar measurements. radar measurements typically control only 3 variables. One is signal-to-noise ratio, mean velocity, then spectrum width. That's all to it, nothing more than that. Only 3 variables, that's all it does. Now, what I plot here is spectrum width on the y-axis here, the number of samples, how it's done. This is a standard error, what I showed here, for a reflectivity or a power measurement. For a fixed SNR, signal noise 20 dB SNR, as we see here, see the spectrum width is, when it's large, you don't need that many samples here. Spectrum width is small, you need more samples because the spectrum width means the particles are fluctuating really fast, giving independent measurement. Hence, we don't need that many samples. If you get basically, typically we use about 60 samples or 80 samples to get an error within about a dB or so. That's typically how we process S-pole data or any other data measurements, what we do it. From the S-pole, it's about 64 or 100 samples, that's what we do it. This is for reflectivity measurement. The velocity, look at this, these curves are concave upward, like this. It needs independent samples to do this. If you do velocity, this is a mean velocity measurement. This is the phase measurement. See the concave downward, they're different between those two. What it needs is, for a phase measurement, we need a correlated samples. And there is a competition in a radar. Power measurements needs independent samples. Velocity needs a correlated measurements. The velocity, again, the spectrum width here, number of samples. If you have 60 samples, you can very good, you can within about meters per second, you can get it. And that's typically how we do that. Okay, this is just a background why we need that many samples so that get a good accuracy of radar measurement. It's not a dB here, it's a meters per second. The scale is wrong here. The meters per second accuracy. You measure wind usually about meters per second. Within a 1 dB, we need about 60 or 80 samples. That's the message from this figure, what I'm showing you here. Okay, now comes a prediction. Can you predict this signal? This is a random sequence of a Gaussian signal. Can you predict this? How does that look like? Let me recall your memory here. This is just a one-time series, what I'm showing you here. This is the in-phase signal, the function of time, 64 samples here, with some definition of mean velocity and spectrum width. This is the I, that's a Q, the spectrum width. This is just one of them. Okay, what is the property of the signal? These signals are correlated in time, depending upon, see, it has a correlation time. It's a function of the wavelength of the radar transmit, the spectrum width. Typically, this time is about 10 milliseconds for S-band radar. For a C-band radar, about 5 milliseconds. It depends upon the spectrum width. But what you see here is, this is basically correlation. It's a Gaussian signal, function of correlation time here. That means these signals are correlated in time. It's not totally decorrelated, pulse to pulse. This allows us to predict the signal in the future, depending upon how we do that. This is for I and a Q. If you measure only for I or a Q, which are components of those complex signal, that also has a similar correlation function like what you see here. That's a Doppler phase shift here, what you see it. And so radar signals are correlated in time to a certain extent, not quite a bit, to an extent. I'll show you how. That's the correlation function of the radar signal. That's the time here in milliseconds. These are two different spectrum width. The blue, 1 meter per second. 2, the red is a 2 meters per second, the spectrum width. Broader the spectrum width, signal correlate really fast, like you say it. It correlate much faster here. Smaller spectrum width, correlation is slower. That means it have enough dependent samples. And this is a typical characteristics of a radar measurement. Now, based on this, there's a rationale to predict the radar signal. What are the rationale here? Radar detects a limited range of mean velocities, about 500 discrete values. For example, in the S-band, all we measure is plus minus 25 meters per second. About 50 meter is our dynamic range, what you got. Even if you measure the 10th of accuracy, talking about 500 different mean velocities, that's all we have. Okay? Doppler spectrum, 0 to 5 meters per second. Even a 10th of a meter, about 50. All we have is 500 times 50, about 25,000 combinations of I and Q. That's all we have. It's not that big. The population of I and Q is finite. It is not infinite, which you can't predict. It's a finite. Radar time series is correlated in time, like I showed you. It has a Gaussian correlation. So these two properties, they are a finite set, and also its correlation in time, that basically makes it radar signal prediction. This is the basis for that. Okay, how we do that? There are many tools for this prediction. In statistics called ARMA, auto-regressive moving average, auto-regressive integrated moving average, ARIMA. These are all there. But I took a different approach. I used the AI. Reason being, for me, I had a hypothesis. I can predict this, but I need a tool simple enough to show, yes, I can predict that. And thought, looked around, I found neural network can do this. AI can do that. I'll show you how. Neural network AI, we talk about, is a crucial component of AI. That's all it is, a neural network like this. You have some input, output neuron, you got the layers. These are all very standard. It's not something new. We have been using neural network for more than 40 years. Of course, recently AI has become a big value. Everyone uses AI, neural network. Neural networks are very ocean. We have a network for detecting the objects, like between, cat and a mouse or something like that. Then estimating something or time series. Neural network is an ocean there. You look at it for language models, so many things. Specifically for this case, I'm using a recurrent neural network called RNN. RNN is architect to pass a time series. Even in that specific, I'm going with a long and short-term memory network. This is a specific neural network to process time series data. This is very well established in the literature, the community. I'm not coming to anything new. They're all available, already exist there. I use that existing tool to show, yes, we can predict the time series. Okay, now the LSTM is the key here, long and short-term memory. What is that, long and short-term memory? Short-term means recent inputs. Say in a paragraph of words, last few words in a sentence called short-term memory. Long-term means it's a word of a paragraph that fits the context. In this time series has two things. It has the long-term trend, the short-term oscillations. This LSTM has the capacity to understand the long-term and the short-term. It has 3 gates: input gate, forget gate, output gate. This controls how this LSTM does work. Okay, that's all the basis. I'm using a very simple existing neural network. This LSTM is I'm using a software. If you go in the market, there are ICs. It's called application-specific ICs, ASICs, available to do the same thing in a hardware. We can do that. It's a software that I'm showing here. Okay, now if you recall, this is a time series what we have. One of them like this. then I under Q for a given mean velocity spectrum width. That's all we define in atmosphere, how the things are moving, how the things are fluctuating. That's all two things. With that, I simulate a signal like this. Like this, we simulate about 10,000 of them, various combinations of mean velocity and spectrum width like that. And that will look like this, like I showed you earlier, the histogram of those 10,000 samples here. I under Q, under phase, all those things like that. Simulate this time series, then train the network. Out of 10,000, 90% of them are used for training. 10% keep it aside for testing. That's a very standard method in AI or neural network. 90% is for training it. Once you train it, you want to make sure that does it work. Okay, conceptually, how does it look like? The conceptual AI radar, according to that. This is the existing radar. Either S-pole, HCR, or wind profiler, doesn't matter, one of the radar. This is the network talked about, LSTM. This has been trained to predict the time series that comes. This measures basically a time series, a small subset of it. Then this will extend that subset into longer duration here. Then radar processor, then other things are formed here. Basically, high temperature spatial measurements are done from here. And so this technique, what I'm showing here, is very unique because the AI most of the time used for just for analyzing a model or a data set. But here, it is in real time. You combine with the measurements of a radar with AI that works right there, then produces the long time series. What is advantage? Instead of spending X amount of time, now you can collect the data in 1/4 of the time, 28%. That means you can do these measurements in 1/4 of the time what you do it today with this technique. That's what it's going to show. Okay, once you train this, we got to validate, does it work? Okay, I'll show you an example here. This is, we have two graphs here. This is the in-phase signal here, the quadrature signal time series. What you see is a black. The black is original time series, okay? There were 64 samples. This technique uses, see that 16 samples here, that's all it does. From that, the red one is predicted. See how close it is. This is, we know the truth because it's all simulated data. I know what the truth is. I'm validating with known set, which is not used for training the neural network. This is a test data set. Same thing with the Q. See how good it is. Now, what's the difference here? Mean velocity, the original data set, 14.6. From this synthesized data, is a 14.8. Spectrum width, 0.96 to 1.35. They are quite close to each other. All I used is 16 samples of the measured data subset. Then red is all predicted. I didn't use all 64 samples measured. I used still 64, but I used only 16 of measured, rest all predicted. This is just one I and a Q time series. I have to show you more results to show convincingly why does it work. Okay, someone could say, what happens? I got only 16 samples here, time series data. This is 16 plus 48 is what I did that, because I took the 16, 48 predicted 64 samples. What I show here is a power measurement. The y-axis here is a partial time series, which use only 16 samples. This one is predicted time series, which is 64, but 64 has only 16 of measured, 48 predicted. I have a 50 different data points I show in this one time series, in this case. See here, RMSE for the 0.2, RMSE for the 0.1. The partial time series doesn't have a good accuracy. We know that based on the thing, what I showed. For 64 samples, we use it, RMS reduced to 0.1, about 50% reduction from what you see here, what you see there. Now, mean velocity. This is again a partial time series that uses only 16 of them, RMS 1.9 meters per second. This is 16 plus 48, 0.4 meters per second. And there is a value what this neural network giving us in this case. We use a subset of only 16 of them, then did the 48 and show it does work. Now, the spectrum width, same thing. 16, if only partial 16 I and Q samples, that's how it look like this. Okay? This is the truth in the y-axis, of course. Sorry, x-axis. This is a predicted time series. See how good it is? There's 2.6 meters per second here. Is a 1 meter per second RMSE. Hence, these are all very well known because these are simulated data. Hence, I have the full control of what I did here. Now, real test is, does it work enough for measurement? That I got to show. Otherwise, won't be convinced. I took the NCAR data. This is from Florida, one of the cyclone measurement, where I applied this, predicting the I and Q from the measurement I and Q. This is the true actual data from 64 hits. This is using only 16 of them, 1/4 of it, plus predicted 48. You see how good are they? This is the cyclone measurement or hurricane over the ocean from NCAR. It's a low PRT case, PRF case. And they're almost identical. How identical are they? This is the truth, okay? This is predicted using technique what I'm describing today. That's the difference between truth, predicted versus truth. See this one? That's the difference. Histogram of that one is here. The mean is 0.1%, standard 26.7%. How much data in this whole pixel? There are close to about more than 10,000 data points in this one. It's not just one or two, what I showed you earlier. More than 10,000. And each of them has a 64 signals, what measured. But I used only 16 of it, subset, predicted 48, and computed that. It does work, at least in this case. This is same case, it's a different example. This is, NCAR scans really fast compared to S-pole. S-pole scans about 10 degrees per second. NCAR do about 30 or even 25 degrees per second, much faster. And they use less number of samples, only 22 samples they use it. What we did, took the 22 samples here, synthesized. 6 is the only thing what we use from this one. Then 16 as predicted, 22 computed same way. Again, the results are comparable. What's the difference between previous one and this one? 22 samples means you get a 1 degree beam. 64 samples means you get a 3 degree beam. That's all the difference is. But actually, spatial resolution. And so the technique seems to work. Whether it is 22 samples, I use again 1/4 of it. 16 is predicted, still does work. What's the difference in this case? That's the difference between predicted and true values of reflectivity. That's all to it. This is not perfect. This is not 100% true, 100% correct. But I'm showing a pathway where you could use this technique to improve your spatial and time resolution. Factor of 3 or 4, which is unheard of, what we can do with this data set. Okay, now let's see what we can do in EOL instruments. We have a lot of radars in EOL, S-pole, cloud radar, wind profilers. They're all measure time series. And this technique applies to any of this radar. It doesn't matter because this technique works on a root level of a signal, the I and Q, which is a root of the radar's measurement. It's not working anything else. The level 0 data, which is the root of any radar measurement. Wind profiler, right? Wind profiler, we have the 915, 449. Typically, it takes about 10 to 30 minutes or 1 to 10 minutes. That's how long it takes because you're taking a lot of averaging in a clear air radar and very low signal-to-noise ratio signals to get a good signal. Now, if you use this technique, you can do this measurement in 1/4 of the time. I haven't done that yet, but I guess it could be done. It's not a problem. It's a matter of someone spending a time on this, working on that. And so this technique has the value for wind profiler. Similarly, if you look at cloud radar, I showed this data earlier. This is on an airborne platform. It's a 3-kilometer stratocumulus cloud. Take the measurement. It's about 5 minutes, 42 kilometers of the measurement is taken as the airplane flies. What's the limitation here? All it does is it doesn't scan. Even though we can scan the data, we can't scan. If you scan it, you get gaps in the measurement because it takes, by the time you go, there'll be gap in your measurement. But if you use this technique, then not only we can get the same accurate data set, also we could scan the cloud radar, get additional measurements along the pathway. It's not just only section. We can do more measurements. And it has applications in airborne radar or ground-based radar, any of them. Okay, so far I talked only about the radar. I said geophysical measurement. What does that mean? I was curious, does this work for a passive measurement? Does it work? I and Q, passive measurement. The active measurements are radar, where we transmit a signal, then receive something and measure it. But the passive measurements are no transmission. It measures just emission from the atmosphere, or a solar measurement. S-pole had a good collection of solar data. It's just a passive measurement from sun. That's all to it. I didn't have access to radiometer at this point. In future, if I have to, I'll do that. So passive measurements are no transmission. It does only the emission or solar or something like that. How does it look like in a passive measurement? It's only a receiver. The antenna here measures the LNA, measures the I and Q. It does all this brightness, temperature, or signal. That's all to it. It's the same thing, same as radar receiver, except the radiometers are very broadband. They're about 100 megahertz. Radars are 1 megahertz bandwidth typically. Radiometers are much broader bandwidth. There's a reason for that. And so the I and Q here is very similar in nature, like what we measure in the radar. But the statistics are much different than radar. That comes to that later. This is an example of a solar radiation measurement from S-pole. What I show here is number of rays here. This is the black is the measured. The red is predicted. This is the I, that's a Q. I did not simulate solar signals. What I did was, they take a lot of measurements in solar measurements. I took one of those files. I used that to train my neural network and use that to predict that. And so I didn't have a simulation capability of solar measurement. I just use a measurement to train, then use a different kind of observation to test it. It does work. But Q is not that good. See, the eye seems to be okay, Q is not that good. And there is a potential. We could even try, explore whether we can do passive measurements. Why it is important? That's the constellation of GPM constellation. GPM has a basic radar in this one. This is a NASA. US has basically a 2 wavelength radars in this one, 14 and 35 gigahertz radar. See how many radiometers around it. It's all radiometers here. And there are not that many radars in the space. There are few, not that many. But still, this technique applies to radar. Then if it does apply to satellite, like this, all those passive measurements, it's a huge advantage for anyone to look at this data set. Then think about this. The satellite typically moves 7 kilometers per second compared to radar and ground-based. It's a stationary. Then you compare to a C-130, about 120 meters per second. They're all moving platforms. Moving platform, if you have some other things, you have very limited time to get your measurements done. Then if you use this technique, then we have a lot more flexibility, how much you want to scan, how much you want to collect the data set. And this will be a game changer in remote measurements, whether it's active or a passive measurements. Okay, I come to a summary slide. What I showed so far, it's the AI, which is basically a neural network. In this case, LSTM has the potential to predict the I and Q. I showed the validation using the simulations. Then applied to a NCAR data set, shows the promising. A lot more work to be done. I'm showing just the potential, how much it has. That could be used for improving spatial or a temporal resolution of EOL radars and wind profilers. The factor of 4 minimum, it could be even more depending upon how we do that. The level 0 data, this is the data route to radar measurements. Then radiometer, I haven't done much except I showed you just one ray, a solar measurement. I have a lot more data. I trained the network on many different ways. I used it for simulations, I trained it. I trained it with the measurements. I have many different networks I have it. What I showed just one incarnation of network, what I used it. I tried many things. I worked on this in the beginning for about 3 years ago. I thought signals are correlated. I should be able to do this prediction. But I was not sure about it because no one has tried before this. I thought a slippery slope getting in there. Then as we get more and more, I got a good, encouraging result as we worked on that. Then slowly I caught up with this. And so it took a while to overcome many hurdles what I faced because I'm not expert in INQ, time series data, or neural network, any of those. All I had was there's a hunch. It could be predicted. That's all to it. But now, what I showed is very preliminary results. It works for instruments on the ground, or airborne, or spaceborne platform. It doesn't matter where the instrument is. We are talking about I and a Q, which is the radar measurements, whether it is an airborne platform, or ground-based, or spaceborne. And so this more like there are presentations like a research where people work on this like an onset of cloud, drizzle or something like that. The research presentations, people work on that many years to refine it. That's more like a research. But this is more like a innovation. It has a potential to expand. And this opens a huge possibility for engineers in NCAR or other places in NOVA to make use of this to make the instruments totally high temporal spatial resolution without changing much of their architecture, except you need to add a small component that's called LSTM network in that process. That's all to it. And so this has a practical application for any instrument that helps us to come up with high temporal or spatial, how you want to do this. So I would stop here. If you have any questions, I'm glad to answer.
Thank you very much, Vivek. That was thought-provoking and interesting. So we'll take questions online and also in the room. If you're in the room, I'll throw this at you. This is a microphone. And if you're online, please use the Slido.
Hi, thank you. Thank you, Vivek. That's a great vision for the AI application in radar system. I have one question about the learning process. The LSTM you train for the model. Do you supervise training to the LSTM from your data? Or if so, how do you classify the train data as the answer that for the model train? Or if not, then how do you process that? That's my
I mean, the training was the testing you're asking? The training?
Yeah,
the
training. Yeah, if the supervisor trained,
Yeah.
then you need to label the answer. Then how do you label and from the
Yeah, I mean, I have a full control of what I did. I have a 10,000 time series data. I pick only 9,000 of them to train that. 10,000 I kept it aside. I don't even touch it. That's for testing purpose. That's a very standard any AI technique. You have a set of data where you know the truth. Okay, important thing is how it does it. I don't think I went into that detail because lack of time. How the LSTM does work, it takes the first n samples, say 16 of them in this case. You do the 17th one. Then take 17 samples, the 18th one. It goes like that, in a locksteps like that. And it does by one after other because this time series is correlated in time. That's why it does like that. In this time series prediction, it's done in many places, like a stock market. Think about how many variables stock market has, maybe 1,000 variables. What you're talking about is only 3 variables here. All we have is mean velocity, spectrum width, signal noise ratio. That's all it is. It's not huge. It's about, I would say, about 1 million different time series data. That's all exists. It's a finite set population-wise. And it's not that big a problem, to be honest, to predict a time series data set. The neural net is a key in this case because it does not only uses the correlation of the time series data, it also knows that long-term, short-term. That means a long-term means a trend. Short-term means oscillations. It reads all the things. That's how neural nets are trained for. And this is very ideal to do that kind of work. And so I could have used many other technique, but this is much simpler for me to prove the concept. If someone wants a different technique, welcome to do it. It's just a tool. That's how I'm using it.
Thank you.
Welcome.
Can I have a second short question? Oh, sorry, that should be short. So for the training part, you use the synthetic data that you produce. Also, you have taken measurement
Correct.
data. So do you, during the training process, do you mix these two to generate your model, or you just use synthetic and predict with the measured data? Does it match, or what's your strategy for this research?
The network what I have is trained based on what I simulated. And the network is what I simulated, what the net is. I'm using the same net for all the things. I'm not using changing the net for one other measurement. I have a net. I can use that for any of the things. For S-band. If you use for a W band, it will be different net. For wind profile, different net like that. It will be different depending on frequency, but just a one net. I'm not changing the net anytime. Yeah.
Okay, thank you.
Thanks.
Really, really interesting talk, and I could certainly think of a lot of ways to take this further with kind of iterating on the ML portion, but a couple questions that came up. One, is the level 0 data publicly available anywhere for like NextRad and EOL data? Like it's not on AWS, but is it like sitting in some NOAA tape drive somewhere? Or?
Yeah, Mike Dixon could answer that. How much NextRad data we have in queue? It's asking for this level 0 data. Yeah, we have tons of data.
From the campaign store, right?
Oh.
Yeah, we have all these things. We have not only for YesPol, we have a cloud radar. All the INQ, Chris Berhardt here, right here. We store all those data sets just for this kind of applications, maybe in the future. We didn't know that, but we have those. NextRad is a whole library of, there are 160 NextRads. They all archive the INQ. And we have tons of data if you really want to work with that. Yeah, go ahead. Yeah.
To clarify that, not all of it. They don't normally record INQ. They have specific data sets, but there's a lot of them. You go on the NCIE and you can find enough time series to choke on.
Okay.
Yeah.
Yeah. The other question was I guess with like real world data, you have like radar artifacts and like all the various ground clutter, anomalous propagation, whatnot.
Correct.
Do you think is there how much do you think that it's important to incorporate some of the, like being able to filter out some of those kinds of examples from the radar, or would you want them in there and then filter them out downstream because there's already techniques for that, presumably?
Okay. Yeah.
Might you get a similar benefit from an interpolation model rather than an extrapolation model amongst your 6 samples or your, the first samples?
I interpolate between the time series measurements.
Yeah, you'd still get more points, and so the average, the noise and the average would go down. But you'd just be interpolating rather than extrapolating many cycles out, which surely can't have very much information from the data coming in.
I haven't tested that, but I will tell you this one. I showed these results about 8 or 9 months ago to Dusan Zernik. Some of you know he's written a book. He said very impressive. He said, asked one of his staff in Oklahoma, said, could you share all your programs and codes to this person, David Schwartzman? He's one of the key person working on many of this. Said, I all the codes. He said, well, very interesting challenge to work on this. And replied back. And this is, even though I didn't publish data yet, a patent was filed for this because it's an UCAR work. But I got a great reviews from Oklahoma, being the center of radar, and getting from Zernik and some other people work on the day in, day out. That gave more encouragement to do that. But coming back to a ground clutter and other artifacts, there are many programs, like John Hubbard could say, how to filter ground clutter. Now, this all comes downstream. But what I'm working on is INQ in the front end, what I'm trying to do it. Whether this INQ prediction, does it work for ground clutter? I don't think so, because I entered only for cloud measurement. Someone has to do it for ground clutter, how the INQ look like that. Maybe it's possible. I haven't done that. And this opens a lot of potential for engineers to look at various scenarios, what they want to do with this. Yep.
Yeah. All your simulations were done for a very nice, well-behaved simulated signal with a Gaussian distribution in the spectrum. If you take a look at a lot of radar data, many of those spectra are not going to be Gaussian looking, and in fact, there'll be a lot of them that are.
Okay.
They have two distribution points.
Okay.
Maybe one from ground clutter and another one
Okay.
from weather,
Okay.
or you understand the question.
Yeah. Okay. I tried this. I know this very well, what you're asking. The simulation is simple for Gaussian spectrum. That's how I channel with this. But to test this, remember, I have network even with the measured data, which is, like you said, it has a non-Gaussian spectrum. I have the network there also. It does work. So I can use the measured data. Don't worry about any simulations. Measured data, train the network, and do it. But I'm not saying I solved all the problems, but I have tested all these things. It does work. And so measured data has all sorts of spectrum, double Gaussian or highly complicated problem, everything like that. In fact, I didn't show many. I worked on the more than 3 years, only on the weekends and evenings, because I was not sure I'm going to get a good result out of this. Many people warn me, hey, you are working on a slippery slope. It's not, people haven't tried this. Don't work on this. But I tried only in my off time, I was working on this. But came out to be a good result. And with this data set, someone interested, they can do a lot more. I'm just saying opening a pathway for engineers to work in the future, how they want to do it. It shows the potential. I'm not saying I'll solve the problem. Think about it. 50 years or more than 60 years of weather radar data exists there. So many groups work on this, many engineers. And this is area, it's not something small, very broad. People know about this. Radar engineers know this in and out. But scientists may not know this because we work on level 1, level 2, level 3 data. Level 0 data is highly challenging. How do you work with that?
Yeah, just to follow up, so
Yeah.
the implications is that obviously with a scanning radar, the statistics of the signal a lot of times may change as you're scanning. You may be going through a boundary somewhere, or there's going to be a large gradient.
Okay.
And so the statistics in those first 16 samples is going to be dissimilar to the statistics that are in the last 48 samples. And
Okay.
so what I heard you just say is that you think it'll even work for something like that.
Yeah, this has been investigated. What I showed was, remember I showed the partial 16 samples, 48 particular samples. I showed about 50 data points I showed. How does it work? It worked 50 data points. Each of them have 64 samples with them. It seems it does work. And it's a matter of digging deeper. All I'm saying is it has a potential. I'm not saying it's a silver bullet for everything. But this opens a new area. NCAR has done many things, for example, right? Color displays, dual Doppler winds, particle IDs. These are primary invention in NCAR. But this is, we have to try it and see whether it does work or not. It needs time. I waited for more than 2.5 years to do this because I was not sure to show any results for you without working with the NextRad data set. Because NextRad data is totally independent, nothing to do with the NCAR.
And I'm sorry to dominate this, but one more question.
Yeah.
So some of the PPI images that you showed did show quite a bit of bias in areas. What's your feeling about?
That's the low SNR values.
Do you think those are all true
Yeah,
with the
low
lowest?
SNR.
I thought even in the high reflectivities there were some biases.
Yeah,
in
I
there.
mean, that's what I'm saying. It's
So,
not
I mean,
perfect
that's-
bullet, but you see how good the comparisons are. That's all.
I want to throw this baby.
Okay, Vivek, great talk. I heard this train of thought for many times, but I think today I have a better understanding, I hope, of the approach. Like any prediction models, is as good as the assumption you make. Okay, so the first question is, have you looked at the spectrum from the first 16 samples versus the full spectrum, including the 16 plus the prediction?
Okay.
I would like to see it and see if my understanding is correct. The second comment is that in order for this technique to work, the first 16 sample must contain something, the essential information. For example, it must give you an estimate of the mean velocity, even though it's not accurate, but it gives you some hint of the velocity before you can use, and a spectral width estimate, before you can trigger your model in order to get the right statistic out.
Okay. Yeah. Yeah. This word, I think maybe I didn't emphasize this plot that much maybe. See, that's the 16 samples versus full samples. And 16 samples is not good enough, we know that. But what is information coming from here is 16 subset. 16 some subset of 16 plus there's an AI with that. That's what that's the trick. It's not just 16 samples all one projecting it. We're using AI as that knowledge. How much knowledge it has, that shows it has some knowledge. That's all to it. Hence, I'm using the 16 of measured data with 48 of predicted data. And that shows that how good that compared to 2 meters per second, 1 meter per second difference. There's about 50 data points in this one. I have about thousands of them. I didn't plot all of them because it may become very spaghetti-looking plot. And it seems to be showing some intelligence, how it does it, and its overall nature. Does it work for polarimetric data? It will, because we're talking about I and Q. I and Q, same HRV, polar, doesn't matter, it'll work. And we're talking about the I and Q, which is root level 0 data we're talking about. And this has a huge potential, depending upon how much you work on that. Like I asked a question about the spectrum look different from 16 to 64. Even if I show the spectrum is very same, as a user, you won't believe that, because finally what you want to know is, does it measure reflectivity right? Does it measure mean wind right? Spectrum wind right? That's what I showed here. And finally the user, they want to know reflectivity, spectrum width. These are things, is it right? Or even user want to know the rainfall, is it right? Because they come from again level 2 data. That's what users want to know. Spectrum width, yes, you can play. And I mean, if there are enough time, we could spend a lot more work on this one, because this area is very broad open. Usually, this type of results are very rare to come by, because this opens a whole new network. Like yesterday I saw in Sundog, you are leading, David Cogney here, doing a, what is called a credit. It's an AI model, weather model. I'm thinking about, wow, you're using some other things like that. And AI is intruding almost everywhere now. And so we have to take advantage of it. This is one advantage. But there's one important difference. EOL being instrumentation centric. It's not just AI. We're talking about AI integrated with a machine. It's like an EV vehicle. I won't call Tesla because people may not like it. But it's an EV vehicle, like that. How a car plus an AI, that kind of thing talking about. And this is a very novel concept, especially airborne radars, where we have limited time to measure anything. Then this will contribute quite a bit. All the scan strategy talk about, you don't need that if you use this one. Thanks for the question.
Well, you've obviously provoked a lot of questions, and I'm sure there are many other questions people would like to ask, but we've used up our hour, and I'd like to respect people's time. But please continue this conversation. Vivek is across in FL1, and I'm sure he would welcome more feedback. So let's thank him again for a very thought-provoking talk.